talk is in-flight absolute radiometric calibration of the LRO wide-angle camera. And the talk will be given by, I hope I'm going to do justice to this name, Prasun Mahanit?
No, it's Mahanit.
Okay, sorry. Well, it's not my fault. It's actually spelled wrong in the program. So. Okay, go ahead.
Thanks. And firstly, thanks to all of you for being here till the last talk. I'm the last obstacle before refreshments. Okay, so I'm going to talk about the radiometric calibration for the wide-angle camera, and I think you have seen a couple of examples of our beautiful images from the LROC cameras, and this is for the wide-angle camera. The LROC wide-angle camera has a wide field of view, and those are some of its characteristics. We were getting approximately 150 observations per day, and it's approximately 180,000 observations in total, and approximately 30 months of global imaging. The first useful images we got at approximately around 20th October 2009, and that's what the camera actually looks like. And when the camera takes an image, each of those observations is actually made up of multiple small frames, and each of these frames has this 7 bands. So they vary. So you have the UV bands on the top of the total. This is the whole semiconductor area which works, and then you have the next 5 visible bands here. And a small walkthrough to like one of our best, one of the WAC products so far. So we have a global base map at 100 meters per pixel at incidence angles 60 to 80 degrees. Most locations are covered by like more than 30 observations. We have multispectral coverage, first time in UV. And we have the global DDM from WAC image, which with overlaps at 100 meters per pixel at latitude less than 75 degrees. And we have the photometric maps of the bidirectional reflectance model for the moon, example here for the single scattering albedo. And we have the polar illumination maps. Now, all these products is possible because our images go through a calibration phase, and that's what I'm going to talk about next. So the radiometric calibration, what it does, it links the pixel DN values, the digital number values, to the physical parameters. So we compare the spectra or images from different origins, and when I say that the physical parameters, I mean radians, which characterizes total reflection, the power received by optical system, and the reflection is tied to the material property. Now the flux distribution here seen is not what is reflected. So why? Because what is reflected from the moon is not exactly what gets reproduced directly. So it goes through a long chain of filters. So like you take this, it goes through the optics, and then you have the pixels, which are now square. So that's another stage of filter. So there are multiple stages before it ultimately appears before you as an image. So once the proper scaling for these things is available, then science becomes easy. So we can compare across different domains. So we need a reference to compare all this. We need a reference to tie whatever we're looking from a spacecraft to whatever we are looking for using a telescope on the Earth. And how do we do that? We need a reference to compare, and that's where the ROLO data is used. So the ROLO data is the USGS Lunar Calibration Robotic Lunar Observatory. So the goal for ROLO is to utilize the moon as an on-orbit standard, both absolute and transfer, for radiometric calibration of remote sensing satellite sensors. The need for an on-orbit spectral standard is between this particular micron wavelengths is actually really high. Why? Because the instruments in flight commonly experience changes in responsivity from their pre-launch calibrations, because say for example, things like baking because of the temperature variation, and the onboard systems can degrade due to the space environment. Now, I'll just go through the the wavelength variations for the ROLO and the WAC data. So this is our WAC data, and So the WAC data is varies. So we have the WAC data there, and this is the Rollo spectral coverage. As you can see, the WAC data starts at like 321, and the Rollo starts at 347, which means that if we want to use this data to match something to that data, we will not be able to do that for the first band there. And that's one thing which will come up later. And that's where we use a little bit of extrapolation for the last part of the phase. And another thing which I want to point out here is if you look through the Rollo data, it seems like an inverted comb, right? So the bandwidths of these things are really small. They are really narrow, and this is another thing which comes into effect later. Okay, so we have an observatory there in Flagstaff, Arizona, which is looking at the moon, and then we have a spacecraft which is also looking at the moon. The question is, how do we create these two? So we do something which is the absolute radiometric calibration. We compare the WAC image and the reference image to compute the calibration constant in the calibration equation. So what is our calibration equation? Now, if you think about it, our image formation model is fairly simple. So we have an image, and each point on the CCD device, it is multiplied by the imperfection in the sensitivity of the CCD, and then we add something related to the dark current or the bias of the CCD, and we have your image. Now, if you invert that model, that's what you get as the calibration equation. And in that model, this is what we are after. We want to know what is the value of this so that we can map something from the DN space to a physical space that's in radians or I over F values. Now, suppose we had during the pre-flight, if we had this value set at 1, and then we have a reference for which we know the values in radians, then from the values which we calculate in flight, we can calculate the corresponding constant that our lambda factor there. And yeah, so the reflectivity I over F is something else which we kind of use synonymously with the radians when we require that, and that's just it's just a constant multiplication with the radians. So the steps in the absolute calibration. So the first thing is to select observations. Now we need to select observations really carefully. They should be of the same location because we are going to compare apples and apples which are exact. And they have the same illumination geometry, and the exposure time needs to be normalized so as to get back, since we consider our detectors to be linear, we just normalize by the exposure time. And so that's what we will be actually doing. We have the so we have the WAC image, which is like really small if you compare, and this is the whole Rollo lunar disk. So we are actually looking through the WAC, through the Rollo, across all the different wavelengths of the Rollo. That's what we are going to do. So we have the same region, and we'll be doing this under the same illumination conditions. So we select an image with very similar illumination geometry. So we start with the Rollo data, and we create something called as the backplanes. The backplanes are actually the illumination conditions found out, and we find this out at every XY location on the image. So let's say we take this entire Rollo disk and we crop out a region plus minus 20 degrees latitude out of that. And we are concentrating only on the center, and we find out the position for the minimum emission angle. Why? Because it is directly underneath the spacecraft. We were trying to get as normal as possible, right in the center, approximately close to the 0, 0 latitude, longitude position. And from there, we take these parameters. So once we fix this minimum emission condition, immediately what comes out, the conditions for the emission and the phase automatically gets, we can automatically get that. And then we feed that in a database query, and we get an image which corresponds almost exactly to that. So the central part of the image actually corresponds to this thing very, very closely. So we use this, and then we use the backplanes now to select the regions, because remember that we want to select regions which have near identical illumination conditions. So for the WAC, we also have the backplanes. And as you can see here, the back planes vary here. So this is the incidence angle. It varies between 10 to 60 degrees here. The emission varies between 10 to 30 degrees here, and the phase, it varies. It's pretty close to like 33 plus minus 2 degrees. And as you can see, right in the center here, you have the least emission angle, and for the incidence, the zero value is somewhere here, and for the phase, it's pretty much almost consistent with the plus minus 2 around 33. So now we use this information. So what do we do here? We are getting two regions, brighter and darker reflectivity. So we need to compare across different regions on the moon. So we will get two examples, one which is bright, the other one which is dark. And we find out where the difference between the backplanes of this and the Rollo, we have minimal variation. Okay. So let's say we have the region 1 there. So this region kind of represents approximately uniform geology here, and the region 2 here, which is fairly brighter. And then what we do is that in that region we have all the different wavelengths. Because of the wavelength, there will be a shift at different wavelengths for the actual sampling areas inside that region. And now what we do is that we look through all the different we look through for that particular wavelength across all the Rollo wavelengths. And for Rollo, the positions do not change substantially, and the selected regions match with the WAC regions in location and illumination. So now we have the data set which we want to use further. So in order to compare the WAC and Rollo data, so let's say I take an example of the 415 nanometers band, and I have the entire train of the Rollo 347 to 766 nanometer set there. So the moment I select these two regions, what happens, automatically I have already spatially selected across the Rollo stack all the regions. And then I get a continuous spectrum from the 12 Rollo bands, which is kind of a superset of the WAC regions. I fit a smooth curve through that so as to get the spectral variation. And then I drag in the WAC values to compare with the Rollo. And that's the correction coefficient we get. Now why I say it's the correction coefficient is because this was our second run. So after the mission we did one run and then with the same Rollo data, and this was our second effort, and that's the correction coefficient which we have over our previous values, which seem to say that our values are very consistent from the very beginning. And that's our results. Our current values for the calibration coefficient are these are the updated ones. So the percentage standard deviation is approximately 1% from selection of different locations within the region. The total uncertainty is between 5.1 to 10.1% for absolute radiometric calibration, and which is kind of dominated by the Rollo value. But we need to note that the relative accuracy of the Rollo disk integrated lunar model is 1%. It's not 5%. But we are interested in absolute calibration, so we have spatially resolved data. So our uncertainty is much bigger. And you can find these numbers on the Rollo website. And the correction coefficient in the second iteration are very close to 1, indicating the closeness of the WAC data in radiance units compared to Rollo. That is, our calibration is stable. And last, it's an ongoing process. Additional WAC data is being compared to Rollo to recheck and calibration from time to time, which means it never ends. And the future work, we want to obtain calibration coefficient with respect to the Hubble data so as to tie all the three data sets. That's it. Thanks.
Okay. Do we have any questions? Try to see if there's any hands up. No questions. Well, I think everyone wants to hear. So, of course, we have to go to league first, right? So, all right. So, go to league, and then I'm sorry. We have one question. Yeah,